Hello everyone, in this segment we will learn how to solve a given elliptic PDE in Matlab software. In this lecture I will introduce you to a graphical user interface known as Pde Toolbox. Pde Toolbox is a graphical user interface of Matlab software where you can do physical modeling, okay, where you can draw the geometry of your problem and you can solve the given elliptic partial differential equation using finite element method. Okay, so let's take a two-dimensional steady state heat conduction problem. Two-dimensional steady state heat conduction problem. The problem says the boundary temperatures of the thin plate are shown in the below figure. Find the temperature at the center of the plate. Okay, so at the center of the plate you need to find the temperature. The top surface of the plate is maintained at 150 degrees Celsius and all other surfaces are maintained at 0 degrees Celsius. So obviously heat will travel from the top surface to the adjacent surfaces and also to the bottom. Okay, so temperature will vary in both in x direction and also in y direction. Okay, so this is a two-dimensional steady state heat conduction problem. Okay, so temperature is a function of x and also temperature is a function of y. Okay, so this is your governing equation, dou square t over dou x square plus dou square t over dou y square is equal to 0. If you see the analytical solution, it is a very complex solution. You will get a summation series, summation solution of hyperbolic sine and hyperbolic cosine. So, and it's a sum. The series converges to 0. So, higher the number of terms, more accurate is the solution. If you go by finite difference method, you will get if you take delta x, delta x is equal to delta y, means the derivation, discretization in x and x in the direction of x and the discretization in the direction of y, means the discretization, the problem discretization. If you take del x is equal to del y, okay, so this is your del x, okay, and this is your del y. Okay, if del x is equal to del y and if you solve the problem, you will get the temperature at the center of the plate is the arithmetic mean of the adjacent temperatures. Okay, so but PD in this lecture I will introduce you to the Pde Toolbox, which uses a finite element method to solve the partial elliptic equation. Okay, so let's go to the Matlab software. In your command window, type Pde tool. Okay, so type Pde tool. Okay, Pde tool, all in small letters, and press enter. So it will open up a graphical user interface where you can draw, you can specify the boundary conditions, everything. Okay, so this is your Pde Toolbox. Okay, so this is your sketch. Here you can draw your sketch. This is the, here you can draw your geometry. Okay, the first step is select the type of problem. Okay, so from this you can select your type of problem. So you are going to solve an heat transfer problem. So select heat transfer. After selecting a heat transfer, adjust the axis. If you see the axes are not equal, it is from minus 1.5 to 1.5, minus 1 to 1, and we are not convenient with this scales. We want from 0 to some 0 to infinity and 0 x, from x and y we want the origin always to be at 0, 0. So let's adjust the axis. Okay, so you can adjust the axis limits in options menu. Okay, when you click options button, a drop down menu will appear. So in that, select axis limits. Okay, in axis limits, select x range as 0 to 5. Our problem is from 0 to 2, so let's take 0 to 5. 0 to 5. Okay, apply, close. Now you can see the x-axis is from 0 to 5, y-axis is also from 0 to 5. Okay, so once you select the axis limit, next is draw. Okay, so draw a rectangular square. So let's draw a rectangular square. So just draw a, by left clicking and dragging, you can draw a rectangular square. Okay, so now let's cue the dimensions. So left, I want it to be 0, bottom also I want it to be 0, so that it will go to the origin. Width is 2 units and height is also 2 units. You can give any name, like can give like PDE example. Okay, PDE example, then okay, so it will come here. So this is your plate. Okay, now once you have drawn your geometry, the next step is to give the boundary condition. So click on boundary, go to the boundary mode. Okay, so when you click the boundary mode, your sketch will turn like this. Okay, so these are your boundaries, the red colored ones are your boundaries. So now you need to give the boundary condition. So double click on the top boundary. So when you double click, so you'll get two types of boundary conditions, where one is Newman boundary condition and another is Dirichlet. Newman boundary conditions are natural boundary conditions, where when heat flux is acting, you use Newman boundary condition. Dirichlet boundary condition is a boundary condition when constant temperature is applied on the surface. So in our problem, if you see our problem, it is a top surface is a constant temperature 150 degrees Celsius. So I will use a Dirichlet boundary condition. Okay, Dirichlet boundary condition. So always keep H as 1. Okay, R is nothing but your temperature. So the top surface is at 150 degrees Celsius. So click 150. Okay, then here again Dirichlet, it is 0 degrees Celsius, so it is already adjusted to 0. Bottom also double click and Dirichlet 0. Left surface Dirichlet 0. Okay, so once you have specified the boundary condition, the next step is discretization of the problem domain, or meshing. Okay, you need to mesh it. Okay, so go to mesh mode. Okay, so when you click the mesh mode, you will get some a mesh problem domain. Okay, it's a triangular mesh. Okay, you can refine this mesh, okay, so that you will get a more continuous solution. You can jiggle also, so that you will get more continuous solution. So this is this meshes is enough. Okay, so after discretization, next is solve. Just click on solve button and click on solve PDE. Okay, so when you click on solve PDE, your PDE will get solved and you will get a graphical solution. Okay, so let's wait till the solution appears. So you got the solution. This is your solution. So you can see on the top surface it is almost 150 Celsius, whereas at other places it is 0. So I want to find the temperature at the center, so I can place my cursor on at the center of the plate. Okay, so this is approximately at the center of the plate, and if I left click, okay, at the bottom I can find triangle number 246. Okay, and the temperature is 27.39 1.62 degree Celsius. Okay, so you can play with plot parameters. Okay, so you can change the color map from cool to hot. Okay, you can also see the mesh, okay, grid also, and you can see the arrows how the heat is flowing inside the plate. So let's plot it. Okay, close. Okay, now you can see how the heat is flowing from the top surface to the sides, to the sides of the plate. Okay, from the top surface it is flowing to the left side and right side, and also to the bottom. Okay, so like this you can solve very easily given partial differential equation in Pde Toolbox. Okay, if you want to learn how to solve parabolic PDEs and hyperbolic PDEs, I recommend you to buy my textbook, a handbook of Matlab Programming for Mechanical Engineers, where I have explained very simply how to solve different parabolic equations and hyperbolic equations using different solvers in the Matlab software. I hope you enjoyed this series of lectures. Thank you.